So yeah, so now I'll just walk through an example of how we can apply some of these patterns and practices of responsible AI in a notebook. So first, like you saw, there was a data scientist cycle in the dev environment, and then the MLOps cycle, which was more of the ML engineer or the MLOps engineer. So we'll first see the data science cycle, where typically the process will be, and this is just a very generalizing, and I've taken a very representative data set. I mean, the real world data sets are much more complex, I'm sure. Uh, so you load a data set, build a machine learning model, you log some of the metrics, and for auditing, we would use ML flow. The ML flow would be something that would, so I have ML flow running. So ML flow has a tracking server where you can log your experiments to it. And I'll show the user interface after when we run the cycle. And then at the end, once we are happy with the model, we'll save the model into a data catalog. Now I have used DVC, data version control, for the data and model catalog, but we'll see that that doesn't have to be. There are other tools also available which can do that. And just to recall, a data catalog, basically DVC is basically something on top of Git, where it will let you check in. I mean, you can manage the version of your data, and the actual data set can be in any repository. You can connect it to AWS, you can connect it to Google Cloud, or on your local machine. It will maintain its own versioning on top of Git. So just like Git is good for code versioning, DVC is an extension on Git, which will let you version data set while keeping the actual data set. So you can take a big gigabytes of image data set and maintain the versions in DVC, while the original data set will remain in your Google Drive or AWS S3. You will still be able to manage the versions and access the versions just through a DVC interface. So here, first step would be, I've taken this Kaggle data set, which is for loan prediction. So this is the example that we will take. So this is, so typically you would see just loading Panda from using Pandas loading as a CSV file. So you would want to have some standardization here, where you would instead use DVC and select the version of the data set. So in this case, just like Git, I would say head tilde 4, and this will be the first version of the data set I'll use. And all I have to do is, and this is the path of the data set. This is the BFSI domain, loan approval. And right now my repository is local. It could either be a Git repository or any of the remote repositories. So I'm just going to load the data set. So it went to the DVC, got the data set, and this is how the data set looks like. This is basically for loan approval, where the different loan applicants are there, the gender, the marital status, dependence, education. These are different features. And loan status is a column which will be yes or no. Yes means the loan was approved, and no means the loan was not approved. And of course, you'll see there are some numerical features also, like the income of the applicant, co-applicant income, the loan amount, obviously, and then a bunch of other things that go into this decision making. And now let's look at, I mean, we talked so much about fairness. Let's first look at just the data that we got. We are going to use this data for training. Let's see if there is a bias that exists in the data. So this is basically what this code will do is it will take your data set and plot these curves, which will take your target feature, which is your loan status, and it will say how the distribution is. So between males and females, you see almost like a stand. I mean, though the number of applicants for females is less, but the actual approval rating seems to be same for both of them. Same thing here for married, unmarried. It seems to be the same. So you can say, okay, this data set should looks unbiased, but how do you quantify it? So you'll use this AI Fairness 360 library. This is just the amount of code that you wrote, and this part of code is just to convert your string features into numbers. That's it. So this is the only code that you write. You just import statistical parity difference, give the target variable, and it will calculate the statistical the same metrics that we saw in the IBM AIF 360 demo. You will calculate statistical parity difference for gender and disparate impact ratio for gender, and we see that this seems pretty unbiased. I mean, the ratios are pretty high. Statistical impact ratio should be, the disparate impact ratio should be close to 1, and statistical parity difference should be minus zero .1 and 0.1. And you can always refer to the IBM AI Fairness 360 example to see if this is true. So this is a quick test you would do either using AI Fairness 360 or using something like a just pure matplotlib, and see if the data set is biased. Now, let me, before we go to the MLflow part, let me change the data set. So I have doctored this Kaggle data set to introduce some bias. So this new version of the data set, which is head minus 3, and let me call it version 2. Now this data set is something, so that is the only change you have to do in DVC, because I have checked in this data set. The actual files are on my local machine, but it will automatically repoint your pointers. So you are treating this as if it's a Git for data. So I'm changing the data set revision and the data set name. This is for my internal use. And now I load the new data set. It's again the same features. And on terms of it, it looks like it's the exact same data set. Let's see what the graphs say. So here you can see the stark difference here. Though the number of female applicants were less, but the approval rating for females is distinctly low. So the yes for the females, for the lone status is less, while the no is high, while that trend is not the same for males, like we saw earlier. Same way, the same way for the no trend for the married is also high. So, or the unmarried is high. So that's some of the things that you can see, and you will typically see the same thing reflected, the same exact code when you do the statistical parity difference and disparate impact ratio. You will see the exact same thing reflecting here. Now you will see the disparate impact ratio has reduced, so that there is a bias in the data set, definitely bias on gender, and there is the negative value, the higher negative value indicates there's a bias for gender. So this was the first thing. So a couple of things. One is the DVC. You just have to change the version of the catalog, and just like Git, it will pull in a new version of a data set. And keep in mind, this can happen for a big image data set. You are training like a 1 GB image data. You just change the version, it will go and get the same. So your code template doesn't change. Two data scientists can share the same template. You just change the dataset version, and it will take a different data set. And then a quick test like this using these matrices, you can quickly check for bias in the data. So this was the first part of the demo. Now let's go to the MLflow part, where how do you track this? Now, once you check, now let's build a model and log this metric. So let me go back to the version 1 of the data set. And so now I'll connect to MLflow. So this code so MLflow basically is an experiment tracker. So it has a standard way to define your ML experiment. You can track your metrics, the parameters, and even the artifacts like the data sets and the model that is generated. You can track it, and it will let you do comparison between different experiment runs, etc. So let me do this. I'll connect to this MLflow server. I will log these charts for the data distribution. I will log the fairness matrices. I'm doing a feature engineering here. So getting rid of some of the string values and making them into, normalizing them into zeros and ones, or label encoding them. And then I'm logging I'm getting my confusion metrics, and I'm yeah, yes, please.
There is one question, Doctor. Yeah. There is one question, again by Claudio Cimarelli. One thing I am doubtful, how we distinguish bias with correct correlation?
Bias with correct
with correct correlation, yes.
Right. So, so if I understand you right, you mean you would, I mean, if these features actually correlated to the loan status, I mean, how would you distinguish that? Is that correct? So
yes.
Yeah. So so yeah, that's an interesting question. So what you could do is, I mean, you could do a correlation test here. Now in this pipeline, I have not done that, but in a standardized pipeline, you could do a correlation test and see if these features get correlated to your loan status features. So there is a correlation matrix that you can build, where you can say that, okay, the applicant income is correlated to your loan status. Now, this machine learning model will also tell you the same thing. I mean that the correlation metrics will help you eliminate some features. If you look at your correlation metrics, you may say that some features are not playing a role in the loan status. Then you could eliminate those features. Now, the interesting point is, does your correlation, does gender play a role in loan status? Now, you could build a correlation among that. I mean, I have not done that. That's a very interesting. That could be something we could also look at, where you could build a correlation matrix and you can see if the gender connects to your loan status. And if it does, that means there is a direct correlation. It's not, and the model may be biased. Yeah, that's a good point. I have not done that, but I think using a correlation also is one way you could find bias. Did it answer the question? Was that, or did I miss that? Okay. Yeah, so that was about the ML flow and the bias. So coming back to ML flow, where we were building this matrix, the model. Uh, what we do is here is you create a confusion matrix here, and I'll log that confusion matrix also. And one of the things I've added to this pipeline is your shape explanations. So I talked about how you once your model is ready. Now in this case, I built a random forest classifier based very simple model that will try to make these predictions of your loan status based on the different features. And let's see what explanations it generates. So here using shape library, I can use a tree explainer because random forest is a tree algorithm or an ensemble tree approach. So I could use the tree explainer here and pass the data. And for the test data set, for which I'm getting pretty decent 86% 86% accuracy. What I will figure out is, okay, from the SHAP scores I can see what are the so just like you mentioned about a correlation, which would be something you do upfront, like in the feature engineering. Now once the model is ready, you want to see what is influencing the model's decision. So this is a quick analysis using SHAP, Shapley global explanations, Shapley additive explanations, where you can say, okay, once this model is there, these are the factors that the model is taking into account. It is giving importance to credit history, property area, and education, and the loan amount, which seems fair. I mean, this is another way you could also look if the model that you developed got biased. So what this is saying is ethic, and these are some of the things you would want to put in front of your ethical AI committee for accountability. Then, okay, this is the model that we are releasing in production. This is how the SHAP scores look like, or the explanations look like. So does having credit history, property area, and education and loan amount, is this a good set to focus on? Is my model doing the right thing? And then I can log that and end this run. Now, and that is something what you can do in the as part of the audit report. Now what I'll do is what MLflow helps you do is do a comparison of the runs. So I'll quickly change this data set to the version 2 of the data set and do these runs. It won't take much time. So I'll just change it to version 2. We saw that version 2 had this bias. And then what I want to show is, once we log this, I'll show it in an MLflow screen how these. Now interestingly, you see, even though this data set was biased, we kind of got the same results. We had a pretty good accuracy rate. So having a bias doesn't do anything. I mean, need not do anything to accuracy. So you may still get the same results. So you may be falsely convinced that, hey, my data set is good because I'm getting a uh, good results. Now, few ways to know that the model is biased. One is, like you mentioned, you can do a correlation and see if the gender is playing a role in the loan data set. And second is something like, once the model is built, now let's see how the explanations look for this. Now, if you see the features that were important, credit history is important, fair enough, but married yes is important and gender male is important. So you see the change in the importance of features, that the data set which was biased, when you build a model out of it, you could see that the protected attributes like married and gender, that started playing a role because these features had bias. And now let me just log this to MLflow. Now, what I really wanted to show is, I mean, one is this, that this is why explanations and correlations is important. You can identify bias and you can see the performance of your model. Second part is what I have done here is I have logged both these experiments to MLflow. So typically, when you get a new data set, you may not want to run through like a Jupyter notebook like this. You will have an MLflow kind of a experiment which will be automated. You can actually tie this to your Jenkins pipeline. So the same Jenkins pipeline for your code deployment for CI/CD, you can do that for ML. So once you have a new data set, you could have an automated without any data scientist managing it. You could generate your ML, generate your ML model, and it will MLflow will generate a UI like this for you. So let me just refresh that. So this is the name of the experiment, and these are the last two are the ones that we ran. So I can, and what I can do is I can just compare that. So the last run was for dataset version 1. Sorry, the last one was dataset version 2, and the one before that, which we just ran for dataset version 1. And let me just do a comparison. Now, head to head, it will tell me the disparate impact ratio for the version 2 was 0.35, while the version 1 was 9.5. That itself, it is telling you that there exists a bias in version 2. And the accuracy you can see was comparable. Uh, though the accuracy fell in version 2, there may be a case where version 2 may have a better accuracy. So this is how MLflow can help you. So once you log the experiment, even though you don't need to do in data in Jupyter Notebook, it could be a Jenkins job, which as probably Amazon's and Google's do. As new data comes in, they would build a model, nightly build of ML model. But how do you verify that these models are actually fair and the data set is fair? So you could go to the MLflow predictions of the model, and while you're logging these artifacts, you can actually log. You don't even need to go to the Jupyter notebook. You could just go here and see how the data set is performing. The same charts that we created, we also log those in MLflow. So you can have a nice intuitive UI where you can clearly see what is happening in your model, and what are the factors that it is getting affected. And again, this is very customizable. So this is just one tool. I mean, you can do the same thing, similar thing in Kubeflow, and you can even write your own API for something like this. But you can, I mean, getting the MLflow artifacts. But this is one way of kind of logging your experiments and getting a good visibility of what is happening in your model deployment. And then the next, so this was about data catalog and checking for fairness. The next part is the actual model. So you can log your machine learning model itself. Now, what I've done in my case is I'm logging this to an S3 bucket. My MLflow is configured to log to an S3 bucket. And now I could have a Jenkins pipeline pull from that S3 bucket and deploy it to production. So I don't even need to touch it. It automatically touch the process. It automatically goes and starts deployment in my MLOps. Or I could just download the model right here in MLflow and use that model. Or I could write a code to pick that model up. So it's very flexible. And the last part here, what I want to show is this model catalog. So MLflow also has a provision. Now we saw in the earlier slide that if you want to log this model, you could do it right here. Like you could, I could check this model into DVC. So the model file, binary file, could be treated as an artifact. I could log it to DVC, and DVC could be my model catalog. That is one option to do it. The second option would be, which is more preferred in the industry, is using MLflow model registry, where here any new model, once I like it, I can check it in, and this for this loan prediction, it will maintain the versions of the model. So when I tomorrow decide to deploy this in production, all I have to do to my Jenkins job is tell it, take loan prediction 1 version 1. It will pick this model from MLflow and deploy it. And if I see, okay, my model is running low on accuracy or there's some error, I could take version 2 and deploy it. So all you have to do is change the configuration, and the MLOps pipeline will deploy these models into production. So that's the advantage MLflow gives you. It abstracts the model experimentation and the pipeline process for you, and lets you push these models to production. So this was the first quick demo I wanted to show on putting the data scientist's hat. Now, in the interest of time, I'll just jump to the second demo, and I'll come back to the chat questions in a bit. Sorry about that. So the second one, what we will look at is, we look at from the machine learning or MLOps engineer persona. So here, what we are looking at the MLOps cycle. So once the model is available in MLflow or any model registry you choose, I want to deploy that to an inference, to a serving environment. So Seldon is very popular for serving, but there are other options like TensorFlow serving. I want to feed live data to it. So typically this would be hosted. Seldon lets you host it as a microservice, and it will monitor the microservice. Now the advantage of having something like Seldon is it will control the invocation of your model. So it will package your model as a microservice, uh, deploy it, and then you can have some patterns for deployment. So you can do an A/B testing. You can say half the traffic of the inference. So when the model is hosted as a REST API, half the traffic goes to one model, one version, other half goes to another version. So you can do an A/B testing right there and there. So Seldon gives you a broker which lets you do the A/B testing. It is even more advanced. You can do more multi-arm bandit. Multi-arm bandit is more of a reinforcement learning concept where you can have multiple options. It's more like from this slot machines. The concept came in where if you have like 3 slot machines, how do you know which one is giving you best reward? So you keep trying those and take your based on the reward, you select that this is the one I want to play more. So the similar concept, if you have multiple 10 different versions of machine learning models, how do you know which one is better? Because your test on your training data, one of them may be doing better, but in real world you don't know. So you may want to do like a multi-arm bandit test on multiple models, and that can be controlled through Seldon. So it's a very powerful tool. I mean, have a look at it. There are a lot of interesting patterns that Seldon provides, which definitely will be helpful to show how the deployment happens. And then the key aspect, what I wanted to show here is the monitoring of the drift. So data and concept drift we talked about. So once the model is in production, how do we monitor the drift to make sure that to understand if the model is not degrading in performance, and then what do you do when the model actually degrades? So here, yeah. So let me start this. I'll go a little quick. Again, the same thing. Uh, I'm I'm choosing. I'm sorry. Was there a question? Okay. Uh, So I'm choosing one data set. Now, what I'll do here is I'll do some basic feature engineering. I'm using this library called PyCaret. I mean, I just wanted to show if you have not already used it. PyCaret is a very good low-code library. I mean, it lets you build an ML model with writing minimal amount of code. I mean, it's relatively new, but it's very powerful. It has all the best practices using different scikit-learn and other libraries embedded into it. So I just wanted to share this because here I could pick up a model from a registry and deploy this, but I just wanted to show you how easy it is to build this model in PyCaret. So just bear with me here. So what I'm doing here is I'm setting up a classification job, and I'm just passing my data set, the one I downloaded from the catalog, telling the known status is this. So it will automatically do all the feature engineering for me. That's the advantage of it. It found out these are the features that were there in my data set. These are categorical, these are numerical. This all it did it on its own. So this is very powerful. All I have to say is yes or enter. And now it created a feature set for me. Now I can do a comparison. Now you must have heard of AutoML, which is very popular, where you compare multiple models in an automated manner. So PyCaret lets you do that. This compare models function actually does an AutoML kind of feature. So PyCaret kind of gives you an AutoML kind of feature where for this particular data set, it is comparing these different machine learning models. And you can go through the documentation of this. These are different approaches, and it is comparing your accuracy, area under the curve, recall, precision, F1, etc. It will clearly give you a leaderboard, just like you have this Kaggle leaderboards. This will give you a leaderboard telling this is the model that is performing. And I can take one of the models. Let me take this LDA model. So I can take LDA as the selected model, and I can do a plot. So just by a single line of command, you don't need to do the matplotlib setup and all. All that is standardized. So it has some very good boilerplate code. It can take care of all your it takes care of all the low level setup that data scientists often spend a lot of time on, and it can give you your ROC curve here. So with a single line of code, and you could change the type of the curve. You could do a precision recall curve or a confusion matrix, and it will give you that. And then just the evaluation of that model, it will tell you for that linear LDA model what was the accuracy, recall, etc. It will give you this thing. So now this was the model that we built. Now, as I said, I didn't have to build a model. I could pull it from a registry or the MLflow registry, but just wanted to show PyCaret. So I took the data set from the catalog, build the ML model. And now what we'll do is we'll simulate how it will be in production. So assume that we have a system that will take my ML model, deploy it as a microservice using something like Selden. I didn't have Selden here, so I didn't install it here, but it's typically something that you would install on something like Kubernetes. It's running on top of Kubernetes, so you could have Selden job running on Kubernetes, and it will let you do the A/B testing and all those things. So here, what I'll do is
sorry, doctor. There is a question. Sorry, by Marco.
No,
when it comes, when it comes to model drift monitoring, do you have any suggestions for situations where we don't have ground truth for future inferences? For example, we recommended something, but we don't have a posteriori label telling us if you got it right or not.
Yeah, that's an excellent question. Yeah, there's no. I mean, that's the problem we always run into for concept drift, that you don't really know what is the feedback that is coming in. Yeah, honestly, I don't have a good answer for that. I have a mechanism. I mean, with something like Selden, when you invoke predict, when you do a predict call to a microservice, you pass the data and it will give you the prediction. You can have a feedback call in Selden where you can pass the ground truth. But how do you get the ground truth? That is not, I mean, that is very domain specific. Because for the loan applicant, like I said, it may take 3 months to approve a loan. So you don't really have that ground truth point at all. So the mechanism is there where you can invoke an API and pass the ground truth, and Selden will use that in its pipeline and help use it to calculate the concept drift. But the actual calculation would be dependent on the domain. So I hope that answered. I mean, to some level.
Yes, thank you.
Okay.
Thank you.
Yep. Yep. So what I'm doing here now is I'm just loading a data set, and I'm assuming that that this is something that will be coming from production. That I will take this data set and I'll periodically pass this data set to my model, and along with that, by some mechanism, I'll have a ground truth also. So I have some data points with ground truth, and using Selden feedback, I'll provide that the ground truth also to my model, and the model will start calculating concept drift, and I'll show that. So first we look for data drift. So I'm using Evidently, which is I really like the good interface they have. So what I'll do is I'll take the data set that was used for training and this new data set, and let me see if there's a data drift. So what Evidently does is it runs some of the statistical tests to check for data drift. So this is just the standard boilerplate code you can write. You just have to pass in your the two pandas data frames, and it will tell you, it will run a KS test for I believe for numerical data, and for categorical it will do a chi-square testing, and it will tell you the p-value of the test. So in this example, it is saying that for gender, property, and area, and and marital status, it is detecting a drift. So the p-value is coming very low. So compared to the training data and the new data that was provided as a data frame, just the one I loaded, there is a definite data drift in these three features. And something like education and self-employed, it doesn't see a data drift. And you can drill down into it. You can see why that for each gender, how much of the data drift is there. So in the new data set, there are more points with the, now I don't know the zeros and ones here, but there are more points with the one gender and the less points with the other gender compared to the reference data set. So this is an indicator of data drift, like the COVID example where the distribution changes. Now, your model may not deviate because of data drift. Now, that is something you would want to check. So in this case, what we would do is we'll take this model. So using PyCaret, I will run a predict model on this new data set. And what it will do is it will give me, I mean, this is the new data set. It will give me the label. These two columns are added by PyCaret when I do a predict model. It will just recreate the data set, the frame that I gave, and it will create the label and the score. So this is the ground truth, the loan status, which of course, I mean, we assume we had. And this is the label that our predict model generated. And this is the score, the confidence level for this particular score. Now using these two values, we'll use evidently and decide if there is a concept drift. Now before using evidently, what I'll do is I'll just do it manually. So I will just print a classification report first. So just for the so with this new data for your for this new data using the existing model, this is the classification report I get. So it does give a pretty good precision recall. So though the data had drift, the data set had drift, the target did not drift. So you actually you're able to generate a good precision recall using your existing ML model. So you don't really need to retrain the model. It is good enough to handle the deviations in the data. Let's see a different view of it. So I'll just plot this the way that a monitoring system would do. So assuming over time, every 10 points, you will calculate a drift and calculate accuracy and plot it. So accuracy over time. So you see, this is a plot of accuracy over time, which is something, I mean, this is the code for it. All it is doing is it is for every 10 points, it is calculating the accuracy based on the ground truth that was provided in the data frame. And you see the accuracy is also very high. So this model doesn't have a concept drift. Now the same thing I'm doing in evidently. So evidently gives you something called a classification report. The only problem is it needs 2 frames. Now this is something that is probably you need to submit it as an enhancement, because it always compares one frame to another. In this case, I just have a single frame, so I'm just so ignore the second value. So it is giving me all the average precision recall. It is giving me the just one of these columns. It will give me the confusion matrix, and it is giving me the F1 score, recall, and precision on this class, which is pretty high. And in this case, red means good. So red is a high score. So it's kind of a interesting color scheme that they use. So and real quick, let me do the same thing on a different data set. So this is a data set which let's see how it looks like. And both these data sets are doctored. So kind of the drift has been added to them. So in this second data set, you see the same analysis I do. We don't have a drift. All the p-values are pretty high. So the same distribution that is there in your training data was given to this. But when you compare this to the ground truth, so now when you're doing concept drift, like the question you had asked, the ground truth is most important here. So now based on the ground truth, you can see that this precision and recall has fallen a lot, because now the relationship between your features and your target has changed. So even though your data is not drifted, your predictions are wrong because your ground truth is different. Now this is a very difficult to track, and like you said, it's very difficult to actually implement this. I mean, this is something we honestly, there's no good solution for this. I mean, if there is a better solutions, I think there's a lot of scope for a better product around this. But this is something we could do is plot this precision recall and see how the ground truth, how the values have reduced. And the same thing with the accuracy numbers. You can now see the accuracy doubling around 0.5 or 0.4% or 0.4 or 40 or 50%. So definitely a drastic reduction in accuracy. So how we typically do this is in a Seldon, the Seldon will calculate this and show it on Prometheus as a chart. And over time, you could clearly see that the accuracy falling down. And you can say, okay, that's something wrong with this. And if there is no data drift, that means the relationships have changed. And then there's a concept drift. And if there's a data drift, I mean, that's a different issue. Then there's a data drift, and that is why your model is not performing well. It will still need retraining. But both cases, you will need retraining, and you will need to compile a sample of data from the real world. And the last is just the same thing what we saw earlier, doing the same thing in evidently, just a classification report. You can see the numbers falling here, 56%, 50%, and now it will be much more blue, the classification report, because of and surprisingly for a single class. I mean, this is odd, but yeah. So now you're seeing the numbers fall a lot. So there's definitely a concept drift here. So this was just an example. I just wanted to show the concept here, how the data drift is measured, concept drift is measured. When you work with tools like Seldon, you can actually see this in practice. You can have a Prometheus dashboard showing the drift and see how how the drift is varied.